Hi everyone, welcome back. This is Debasattam and you are watching EE635 Applied Linear Algebra. This happens to be the fifth lecture and the third and not the final module. For this lecture, we are going to have a fourth module also. So now in this module, what we are going to look at is some further properties of this subspace and this basis idea. We have already seen that a basis is a generating set which is also linearly independent, and from there there were some very nice some very nice, what should I say, inferences that we could draw from the from some earlier results. Things like, for a if there is a finite generating set, then every basis will also be finite and they will also have exactly same number of elements. Using that number, that invariant, we defined this idea of a dimension of a vector space. In the last module, we also saw how such a basis can actually be calculated for the cases of row span and column span. How to get basis in general, that is something that we'll take up in the last module, not this one, the fourth module. Okay, in this one, we will see some more properties of this basis, namely the almost the central idea in every application of linear algebra in engineering practices, namely the idea of a basis extension, right? So the basic idea is this, that I have a big vector space, and in that big vector space, there is some subspace given to us. And somehow, by whatever means possible, I have succeeded in getting a basis for a subspace. Yeah, but my goal is to actually obtain a basis for the big vector space, not just the subspace. How can I do that from a basis of the subspace that I have already found out? This idea of extending a smaller linearly independent set to a basis is the idea of basis extension. Okay, at the heart of this result actually lies a very simple observation, and that is what we're going to see now. Okay, let me try and share my screen. And let's wait when it shows up. Yeah, there it is. Okay, I think I'm still at the companion note. Yeah, so this is the one we are keeping our notes. Where is it? Where is it? Where is it? Yep. Yeah, here. Now, so as I said, at the heart of this basis extension idea lies this very basic observation, which is the following, which we are going to call a lemma. We are also behaving like a mathematician, but it's a good practice to, write your results like this. It's easier to keep track, and it is easier to do cross-referencing. Now, what is this lemma? This lemma once again says that, okay, V is a vector space, is a vector space over a field F. Doesn't have to be finite dimensional or anything. Some, just some vector space. Let V1 dot up to Vm be a linearly independent set. That's okay, no? I can have a finite linearly independent set and then in some, big infinite dimensional perhaps vector space. Right. This is linearly independent. Now, suppose W is a vector in V, but W does not belong to the span of V1 up to Vm. You understand, no? W is some vector which is in V, but it's not in the span, it's outside the span. Then the surprising fact is that if I adjoin this new vector to my already existing linearly independent set, then this new set is also linearly independent. Proof. Like all linear independence proofs, we first assume, take a linear combination, suppose it goes to 0, and then show that this linear combination must be the trivial linear combination that goes to 0, which would prove that only the trivial linear combination goes to 0, which would prove that these vectors are linearly independent. Okay, now, all right, yeah. So how do we do this? Say, consider alpha 1 v1 plus dot 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 up to alpha m vm plus beta w is equal to 0. Yeah. Notice that if beta is equal to 0, then alpha 1 v1 plus dot 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 up to alpha m vm must also be equal to 0. Yeah. But then these vectors are linearly independent. So this would imply alpha 1, this must be the zero linear combination, the trivial linear combination, because v1 up to vm, this set is linearly independent. So if b is equal to 0, then alpha 1 up to alpha n are also 0. Yeah, so we have nothing to prove. This is a trivial linear combination. On the other hand, if beta is not equal to 0, then w can be written as minus alpha 1 by beta into v1 minus alpha 2 by beta into v2 minus dot 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 minus alpha m by beta into vm, which is in fact in the span of v1 up to vm. But that's a contradiction, as in I don't have to write contradiction because I am assuming that w is not in that span, right? Yeah, so this, yeah, it is a contradiction. I said it wrong. It is a contradiction. Okay. Yeah, so therefore, yeah, right. So W belongs to this. This is a contradiction. So therefore, what we had assumed is not okay. So that means beta has to be equal to 0, and then this all the alphas must also be 0 in that case. Okay. So therefore, v1, v2 dot 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 vm comma w must be linearly independent. Yeah, is that all right? Now, so pictorially, it would look something like this. Suppose this is a span of some vectors, and here, if I have another vector outside, right, then this together with this, okay, so suppose I had a vector here and a vector here, then these three vectors also will be linearly independent. Okay, that's it. Now, some consequences of this. First one is this theorem. Once again, simple result, but very profound. It's going to be very important for us. So let V be a finite dimensional vector space over a field F with dimension of V equal to n. Let W be a subspace of V. Then every linearly independent set, linearly independent subset of W is finite. In fact, its cardinality would be, in fact, cardinality is less or equal to n and is part of a basis for W. It's quite a mouthful, but the proof, in fact, is very simple. Yeah, it's actually a very simple result. You see, V is a finite dimensional vector space. So suppose S is a subset of W. Subset. Let um, S be linearly independent, right? Of course, S is a subset of V also because it's a subset of W and W is a subset of V. So S is a subset of V. So then by the earlier theorem in the first module of this lecture, we know that cardinality of S must be less than or equal to dimension of V, which is n. Whatever is the dimension, it's a generating set. So it has a basis with n elements. So if S has to be linearly independent, then S had better have less number of elements less than or equal to n. It cannot have more than n element. In that case, it cannot be linearly independent. Okay. On the other hand, suppose span of S. If span of S is equal to W, then we already have a finite basis for W, right? S is linearly independent, yeah, as well as it's a generating set, spans all of W, so it's a basis. But suppose span of S is strictly contained in W. In that case, this implies there exists a vector, say V1, which is in W, but not in the span of S. Okay. Now consider S disjoint union with V1. Yeah, this is a subset of W, and the earlier thing will apply to this, and this will also be linearly independent. Is linearly independent by our earlier lemma, by the lemma that we have just proven. Yeah, so this we'll consider as our new S, and we once again check if S disjoint union V1 is equal to W or not. If it is equal to W, then nothing to be done. If it is not equal to W, then further there exists a V2 which is in W but not in the span of S disjoint union with V1. So this implies now I will look at S disjoint union V1 disjoint union V2, and that is how I will proceed. Yeah, ultimately I will have a basis for W, say BW, which will be such that its span is equal to W and BW is linearly independent. Of course, the process has to end because this BW must also have its cardinality less than or equal to n. It cannot have more than that because BW is linearly independent. Its cardinality can never be more than n. So that is how we extend the basis. This actually is the end of the proof, and this says how one extends a basis. So somebody gives me a set which is linearly independent, then I keep adjoining new vectors and keep checking the span, right? So uh, till the point arise, till we arrive at a point where the span is the whole span is the subspace that we had started with. Okay, that is how we extend the basis. Now, some immediate consequences of this idea would be, let us see. So yeah. So let me state this as a corollary, but don't get kind of bogged down by these facts that I'm just writing them as theorems, corollaries, lemmas, and things like that. These are just simple observations. What is that? So say V once again is a vector space over F. I'm not writing it, huh? This is just a given fact. V will be our vector space always. Suppose dimension of V is equal to n, so it's a finite dimensional vector space, yeah. And suppose W is a proper subspace of V. Then we must have dimension W strictly less than dimension V. Proof. Once again, because V is finite dimensional, there exists a basis for W, and there exists basis BW for there exists BW basis for basis for W, and this BW must be less than or equal to n. Did I use the number n? No. Yeah, I have used the number n, which is the dimension of V. This is from our earlier result, from the theorem, right? But span of BW, which is W, this is a proper subspace, huh? Remember, it's a proper subspace. It doesn't fill all of V. Because it's proper, this implies there exists a vector V which is in V but which is not in W. Therefore, BW union, this joint union V, this is also Li by lemma, by the lemma that we have proven. It's linearly independent. But by our earlier result, this means BW, this V, this cardinality must be less than or equal to dimension of V, because if it is more than dimension of V, then it cannot be linearly independent. Yeah, but what is this? This is dimension of W plus 1. Yeah, dimension of cardinality of BW is dimension of W. There is one extra vector, so dimension W plus 1. This is strictly less. This is less than or equal to dimension of V. So of course this implies dimension of W is strictly less than dimension of V. Yeah, so if it's a proper subspace, its dimension can never be more than or equal to the dimension of the overall, the bigger vector space. This completes the proof of the corollary. The next corollary, so let me call this corollary as corollary 1, yeah, and then I have another corollary, which is that so once again V is a vector space, over F, and dimension of V is equal to n, which is finite. Then and then let S be any subset of V, which is linearly independent, then there exists a basis of basis for the basis for V that contains S. This doesn't even require a proof because it's something that we have already proven in the theorem. So we have a finite dimensional vector space. There is a linearly independent set. Of course, it has to be finite because the vector space is finite dimensional. So any linearly independent set must have its cardinality less than or equal to n. So S must also satisfy that. So S is a linearly independent set. It's finite, as I said. And then I can just do the basis extension process. Add a vector which is not in the span. Look, that will extend the span by one dimension. If it is all of V, well, nothing to be done. If it is not, then there will be vectors beyond that. Take another vector there, increase your size, increase the dimension of the new span by even one more, and so on. You continue, but it's a finite dimensional vector space. Its basis must be of size n, as we have seen before. All the bases have same size for a finite dimensional vector space. Therefore, this process will end infinitely many steps. Yeah, that's it. That is how you extend a basis. Yeah. It may sound very, but, it may sound very complicated and it's very difficult idea is being proven. Not like that. In fact, if you think about these things in terms of just the Euclidean space that we are all familiar with, then these are kind of very easy to understand, very easy to visualize. What makes it interesting is that by this vector space abstraction, I can now apply these things to all sorts of vector spaces that we have seen, which have finite dimensions, namely not just Euclidean vector spaces of columns of numbers or rows of numbers with numbers coming from arbitrary fields. This will be applicable. Similarly, these ideas will be applicable to matrices. These ideas will be applicable to space of functions defined over finite sets. Yeah, these things will be applicable to polynomials of degrees less or equal to a given number. They are finite dimensional vector spaces. So whenever you have finite dimensional vector spaces, all these things that we have learned about basis extension and things like that is going to work out. We're going to end this module with one more interesting result, which will be very useful for us. And that will also be instructive in the sense that we are going to see our first glimpse of a proof, which is genuinely abstract. Although the result is kind of intuitively obvious, but the proof will be completely, general and abstract. And the proof is the following, and the result is the following. We can call it a theorem, but you don't have to memorize it as a theorem or as theorem as such. It is the following. So once again, suppose I have a vector space V. Yeah, is a vector space over a field F, and suppose W1 and W2 are subspaces of V, subspaces of, both of them are finite dimensional. Then the following is true. Dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2. What am I missing? Of course, minus dimension of W1 intersection W2. Okay, how do I prove this? So as they say in maths, such things always form what is known as a lattice structure. So I have two subspaces, W1, W2. They may not contain each other, they may not even be related to each other in any way, but they both will contain W1 intersection W2. This is the subspace, this is the largest subspace that is contained in both W1 and W2, like an LCM, as I see very soon, like a GCD, as I see very soon. However, they both are contained in this sum of two subspaces. So that is the basic lattice structure. Now, what we are going to do is we are going to take, okay, we are going to take, say, V1 dot dot dot. So so because you see, W1 is finite dimensional, W2 is finite dimensional, W1 intersection W2 is contained in this two finite dimensional vector spaces. So W1 intersection W2 will also be finite dimensional. All right. Then V1 up to say Vk be a basis for W1 intersection W2. Okay. Now, so this I can extend to a basis for W1, and similarly the same thing extended for as a V1 Vk and say x1 dot 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 up to xm to a so this is a oops this is a basis for W2, right? So I had this a basis for this subspace of W1, so I extend this here and I extend this here, same basis V1 up to Vk, yeah, that I extend for W1 and also extend for W2, and that gives me this x V1 up to V1 up to Vk, and then W1 up to WL, and then V1 up to Vk, x1 up to xn. With this, what does that mean? Of course, dimension of W1 is then equal to K plus L. Dimension of W2 is equal to K plus M. And of course, dimension of W1 intersection W2 is nothing but K. This just follows from the earlier results and the way we have constructed. What we are going to claim is now that this set, so claim V1 dot 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 up to Vk, W1 dot 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 up to WL, and x1 dot 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 up to xm. This set is a basis for W1 plus W2. This is the claim. Okay. First thing, what do I have to prove in order to show that this is a basis? I have to show that it generates, and then I have to show that it's linearly independent. So first thing, this indeed is W1 plus W2 to show that. This is in fact obvious. Why? Because say, say what should I use? Say W is a typical element in W1 plus W2. So arbitrary element, yeah. By definition, this implies W must be equal to W1 plus W2, where W1 belongs to W1 and W2 belongs to W2. Yeah, so this implies W1 is equal to some alpha 1 V1 plus dot 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 alpha k Vk plus beta 1 W1 plus dot 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 up to beta L WL, and W2 must be equal to gamma 1 V1 plus dot 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 up to gamma k Vk plus delta 1 x1 plus dot 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 up to delta m xm, right? Right? So this then implies W1 plus W2 is equal to alpha 1 uh, plus gamma 1 into V1 plus dot 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 up to alpha k plus gamma k into Vk plus beta 1 W1 plus dot 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 up to beta L WL plus delta 1 x1 plus dot 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 up to delta m xm, which of course is a linear combination of the given vectors, no, of these vectors. So therefore, this obviously belongs to span of V1, Vk, W1, WL, X1, Xm. So the fact that it's a generating set is proven. Now we have to prove that this set V1 up to Vk, W1 up to WL, and X1 up to Xm is linearly independent. Yeah. Once again, how do you prove linear independence? Take a linear combination and show that it's the and show that if the linear combination is equal to 0, then the linear combination has to be necessarily the trivial linear combination. Okay. So consider alpha 1 V1 plus dot 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 alpha k Vk plus beta 1 W1 plus dot 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 beta L WL plus gamma 1 x1 plus dot 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 up to gamma m xm, and that is equal to 0. Okay. Now, first thing that we are going to notice is this implies gamma 1 x1 plus dot 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 up to gamma m xm. This vector now is equal to minus sign in front, alpha 1 v1 plus dot 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 up to alpha k vk minus beta 1 w1 plus dot 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 up to beta l wl. But now therein lies a problem. Problem as in some observation. Okay, okay. You see, this guy out here is a linear combination of x1 up to xm, and these are vectors from where? These are vectors from W2. So this, of course, is a vector in W2. On the other hand, this is a linear combination of V1 up to Vk and W1 up to Wl together, which forms a basis for W1. So that means this vector is there in W1. So I have two vectors which are equal to each other. So it's a single vector. That single vector, the left hand side, so the identity, the left hand side of the identity says that this vector must belong to W2, and the right hand side of the identity says that the same vector must belong to W1, right? So which means this vector must belong to W1 intersection W2, right? So this implies gamma 1 x1 plus dot 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 gamma m xm must belong to W2 intersection W1. But we have already a basis for this, which means gamma 1 x1 plus dot 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 up to gamma m xm must be equal to delta 1 v1 plus dot 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 up to delta k vk, because v1 up to vk is a basis for w2 intersection w1. This is because v1 dot 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 up to vk spans w1 intersection w2. Great, no? But then we have already seen that x1 up to xm and v1 up to vk together, that's a linearly independent set because it's a basis for w2, which implies gamma 1 equals gamma 2 dot 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 up to gamma m must be equal to 0. I've skipped this step. Let me write that down. This implies gamma 1 x1 plus dot 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 plus gamma m xm minus delta 1 v1 minus dot 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 minus delta k vk is equal to 0. So this linear combination goes to 0, but since v1 dot 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 vk x1 dot 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 xm, this set is Li because it's a basis for v2. So what I have gathered from here is that gamma 1 up to gamma m are all zeros. Putting this in equation 2, putting this in equation 2, we have already obtained that gamma 1 up to gamma m must be 0. We obtain that alpha 1 v1 plus dot 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 up to alpha k vk plus beta 1 w1 plus dot 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 up to beta l wl must be equal to 0. But then this implies alpha 1 alpha 2 dot 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 up to alpha k equal to beta 1 equal to beta 2 dot 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 up to beta l. This must be equal to 0. Why? Because v1 dot 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 vk comma w1 dot 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 wl, this set is linearly independent because it's a basis for x1. So all the coefficients are 0, which means I take a linear combination, I claim that it's a 0, implies that only the trivial linear combination is 0. Therefore, those vectors must be linearly independent. Okay, no? This completes the proof. Oh, sorry. Sorry, my bad. This just proves the claim. So this proves this set, no? This weird set 1 to vk, w1 up to wl, x1 up to xm is a basis for w1 plus w2, which then implies dimension of w1 plus w2 is k plus l plus m. So now to verify this, I just have to look at the various dimensions. Yeah, to verify the theorem, to get the result of the theorem. So left hand side, so this is, let me call this star. So LHS of star is equal to dimension of W1 plus W2, that happens to be K plus L plus M. RHS of star is dimension W1 plus dimension W2 minus dimension W1 intersection W2. So let us write these numbers. This of course is K plus L. This of course is K plus M. This is K. This K will cancel out. This will be K plus L plus M. So this implies LHS is equal to RHS. So proved. That's it. That completes the proof. Okay. Fortunately for this module, there is no immediate attention problems. You can immediately move to the next module, which is the fourth and final module of lecture number 5. Okay. So let's see you on the other side of this break, which will be the final module of lecture number 5. Okay. Till then, bye bye.